Hello everyone. Today I will present our work entitled Mapping FDM Process Parameters to Effective Thermomechanical Drivers in 4D Printed PLA Beams using Machine Learning. The main idea of this work is to move one step beyond direct prediction of the final deformed shape. Instead, we ask whether machine learning can predict physically meaningful intermediate drivers that are responsible for thermal shape morphing in 4D printing PLA beams. Before presenting the motivation, I would like to briefly clarify two terms used in this presentation. First, 4D printing refers to 3D printed structures that are designed to change shape over time when exposed to an external stimulus. In this work, the external stimulus is thermal activation, and the response is the morphing of PLA beams. Second, the terms FFF or fused filament fabrication and FDM or fused deposition modeling are used here to describe the same extrusion-based polymer additive manufacturing process. Both refer to the layer-by-layer deposition thermoplastic filament. The motivation for this study is that thermally activated shape morphing in FDM printed PLA structures is promising for deployable and shape-changing components. However, the final morphing response is not controlled only by the nominal slicer settings. Parameters such as printing speed, layer height, nozzle temperature, and bend temperature are important, but they do not fully describe the internal thermomechanical state generated during printing. During FDM, several hidden variables are introduced. These include residual stresses, layer-dependent cooling histories, imperfect interlayer bonding, and local variations in polymer orientation. These factors are difficult to measure directly, but they strongly influence the final morphing response. The objective of this study is therefore twofold. First, we introduce a physically grounded proxy for the morphing response based on the bilayer effective coefficient of thermal expansion framework. Second, we evaluate whether machine learning can predict this physical proxy directly from the nominal FDM process parameters. This slide presents the physical framework used in this study. The basic assumption is that thermally activated bending can be interpreted using a simplified bilayer model. In this model, the beam is represented by a top layer and a bottom layer, each having an effective coefficient of thermal expansion, or effective CTE. The important point is not only the absolute value of expansion, but also the difference between the two layers. The mean effective expansion controls the overall scale of the response. In contrast, the differential expansion between the top and bottom layers controls bending and curvature. In other words, if both layers expand or shrink similarly, the beam response is mainly uniform. But if the two layers have different effective thermal expansion behavior, this mismatch generates curvature. This difference is represented by delta alpha, which acts as the bending driving term. Therefore, the effective CTE framework allows us to connect process parameters to a physical morphing mechanism instead of treating the printing process as a black box. The experimental dataset is based on FFF printed PLA beams. For each process configuration, three replicate specimens were produced. Six FFF process parameters were varied, that is activation temperature, printing temperature, layer height, layer width, nozzle temperature, and bed temperature. The selected ranges cover the feasible processing window for PLA beam morphing. We can see these ranges at the table on the right side of the slide. For example, we can see activation temperature ranged from 76 to 96 degrees Celsius. Printing speed ranged from 50 to 110 millimeters per second, and so on for the other process parameters. In total, 80 unique configurations were selected. This provided broad coverage of the six-dimensional process space while keeping the experimental campaign manageable. For each configuration, effective CTE values were obtained through calibration against the measured morphing response. This slide summarizes the complete workflow. The process begins with the definition of the FDM parameter combinations and the fabrication of PLA beam specimens. After printing, the beams are thermally activated and their final deformed shape is measured. From the measured morphing response, we calibrate the effective thermomechanical quantities of the bilayer framework. These calibrated quantities are then used as machine learning targets. In other words, the models are not trained directly only to predict geometric deformation. Instead, they are trained to predict the effective physical drivers behind that deformation. The input variables are the nominal process parameters, while the outputs are the mean effective expansion and the differential CT, delta alpha. The models are then evaluated using configuration level out-of-fold predictions so that the reported performance reflects prediction on unseen process configurations. This slide shows the main result of the study. The first target is the mean effective expansion, which controls the overall response scale. For this target, the out-of-fold R-squared values are approximately between zero point 0.2 and zero point 0.3. This indicates a partial process level signal. In practical terms, the nominal FDM parameters contain some information about the average effective expansor behavior, but the prediction is still far from complete. The second target is delta alpha, which represents the differential CT between the two layers and acts as the bending driver. For this target, the R-squared value is below zero point 0.1. This means that the bending driving mechanism is only weakly predictable from slicer level inputs alone. This distinction is important. The overall expansional scale appears to be partly encoded in the nominal printing parameters. However, the differential mechanism that produces curvature is much harder to capture. This suggests that bending depends more strongly on hidden internal states generated during printing. The interpretation is that direct process to physics mapping has clear limits. The machine learning models can identify a partial relationship between the nominal process parameters and the mean effective expansion. However, the same parameters are not sufficient to reliably predict the differential expansion that governs bending. This result is consistent with what is known about FDM printing. The final internal state of the printed part is affected not only by the selected slicer parameters, but also by cooling rates, residual stress development, local bonding quality, and layer by layer thermal history. These are not explicitly included in the available input variables. Therefore, the weak predictability of delta alpha should not be interpreted simply as model failure. Instead, it indicates that the available process descriptors are incomplete. To predict bending more accurately, we may need additional measurements or physically informed descriptors that better capture the internal state of the printed beam. To conclude, this study defined and tested a physically grounded machine learning mapping problem for 4D printed PLA beams. Instead of only predicting the final shape, we attempted to predict effective thermomechanical drivers derived from a bilayer CTE framework. The results show partial feasibility for predicting the mean expansion driver from nominal process parameters. However, the differential bending driver, delta alpha, remains weakly predictable from slicer level inputs alone. This finding supports the idea that nominal FDM settings provide an incomplete description of the internal thermomechanical state. For future work, an important direction is to enrich the input space with variables that better describe the actual printing history of the material. This could include cooling rate indicators, residual stress related descriptors, local boundary quality, and layer by layer thermal history. Such variables may help capture the internal state that controls differential expansion and bending. Thank you very much for your attention.